All right, so we'll go ahead and get started. So we're going to pick up where we left off last time. We're talking about Chapter 1, which is, again, that introduction to electronics, dealing with predominantly with signals and a little bit with amplifiers. I haven't posted the first video yet. I'm going to do that today in combination with this one. So we left off right around here. We were talking about this example. I wanted to go back to it just to do a little bit of a recap and then jump into new stuff. So the cascading amplifier problem or cascading amplifier example. Can anybody explain to me what that's really trying to address? What's the problem that this solution is trying to address? Why not just use one amplifier? Yes?
You may not be able to get one amplifier that has all the various attributes that you want.
Exactly, right? So we're concerned with the impedance matching problem first, and that is whether the input impedance is significantly larger than our source impedance, right? That's one problem that we're dealing with. We want that relationship to be, we want this to be much, much larger than that in order to minimize the effect of this on the gain. We're also concerned with the impedance matching problem at the output, which means that we want this to be significantly smaller than the load. And then we also have the gain to be concerned with. So if we can't find one amplifier that's able to satisfy all of those requirements, then what we can do is use two or more. This amplifier gives us a good input characteristic. This amplifier gives us a good output characteristic. And this amplifier in the middle provides us more gain than we would have gotten otherwise. And so the way that we analyzed this problem was essentially as four different voltage dividers, because that agrees with the way that we model the amplifier. And the math, right, we have the aggregate gain of the cascaded amps, the loss of gain at the input, and we calculated all those values as shown here. Again, these are all just voltage divider equations. We came up with the total value both with and without the loss of gain at the input. We got it in decibels. And then we talked about the roles of the first, second, and third stages, which again, first stage provides the large input resistance, third stage provides the small output resistance, and the second stage provides the more significant gain. Okay, so then this is sort of where we left off. We touched upon it, but I'd like to maybe start fresh from here. So the four different basic amplifier types. These are four basic ways of representing an amplifier. We've so far mostly been touching upon or addressing the voltage amplifier, which has an input voltage, output voltage. We also have a current amplifier, measures current at the input, generates an output current. The main difference going from here to here is that now our output is configured as a Norton type source as opposed to a Thevenin. It uses a dependent current source as opposed to a dependent voltage source. When we move from here to, actually I'm going to do sort of a weird jump from here to here, okay, the voltage amplifier and the trans resistance amplifier look exactly the same, right? You look at them. The only difference is this little piece here. The trans resistance amplifier has an output voltage that's dependent on the input current. Therefore, it's V out over I in, the ratio that we're looking at with regard to gain. And then if we jump from here down to here, again, these two look exactly the same, except for this little piece here, where instead of having our dependent current depend on another current, it's dependent on the voltage. So there's four different permutations of input and output. Your input can either be voltage or current. Your output can either be voltage or current. Now, this here shows us the gain value, V out over V in, I out over I in, I out over V in, etc. That I think we've already made clear. Now to talk about the ideal input and output characteristics. That essentially depends on what you're trying to measure and what output you're generating. Whenever you are measuring an input voltage, you will want ideally you'll want your input resistance to be infinite. And the reason for that is such that there's no current flowing into the amplifier and there's no voltage drop along your source resistance. When you're measuring a current, for example here, you'll want your input resistance to be 0 because if we had an infinite input resistance, essentially no current would flow in and we wouldn't have anything to measure. Now jumping to the output, when we have a Thevenin type output, our ideal resistance, output resistance is 0 because again we don't want there to be a voltage drop along that series element. When we are generating an output current, we want the output resistance to be infinite because we want all of the current to flow out and none of it to flow along this shunt path which remains inside of the amplifier itself. So you can boil it down to simple rules. Input voltage, ideally infinite input resistance. Then you have the opposite case. Output voltage, ideally you have a 0 output resistance, and then you have the opposite case. Now we said that all of these cases are equivalent to one another. We didn't really go into the details of how that would work. So I would like to go through one example of that. So let's take a look at the conversion between AVO and AIS. All right. So we know that this is essentially a Thevenin to Norton conversion. Unfortunately, I guess I could show one on one screen, one on the other. So let me do this. Okay, so now you can see both. All right, so let's say that we're trying to go from the current amplifier to the voltage amplifier. We're trying to find the equivalent gain between those two. How would we convert the current amplifier to a voltage amplifier? So we start off with a Norton type source at the output, right? So we know that our I Norton is equal to AIS times II, right? That is the output current for the Norton source. The Norton resistance is called R0. Okay, now we want to take that, so this looks like this. I'm not going to draw it as a dependent, it doesn't really matter. We have something that looks like this. We want to convert it to something that looks like this, right? This is I Norton, this is our R Norton, this is going to be our V Thevenin, and this is going to be our R Thevenin, but we know it's going to be equal to the R Norton. So first off, right, we already know right off the bat this is equal to R Norton. How do we come up with our V Thevenin? V Thevenin will be equal to I Norton times R Norton. That should be familiar. Okay, this is just what we learned from ELC251-02 about how to convert between Thevenin and Norton, Norton and Thevenin sources. We plug in the values, and what we end up with is AIS times AI times R Norton, and that gives us our V Thevenin. I am going to use this right here. Okay, we called in our diagram, we called R Norton R out, and so I'm just going to go ahead and call it R out at all the spots in here. Okay. Now, how do we align this with AVO. Okay, we know that AVO, if I bring up, okay, the picture here. So V out is equal to AVO times V in. So what we need to do is we need to take this I in right here and we need to put this in terms of V in. So how do we do that? We can just go ahead and use Ohm's law. We know that I in is equal to V in divided by R in. And so what that'll give us, if I scoot over just a little bit, is AIS RO over R in, all that grouped together, times V in equals that right there. And so this is our equivalent AVO. And so if you look, now I'll switch back. To this, right, we see that we do have interchangeability or equivalency between the different amplifier types. So the 4 types exist. We can convert between any of these. And so the gain for the voltage amplifier is equal to the gain for the current amplifier times the ratio of the output and input resistances to one another. And you could do something similar for all the rest of these different cases. So that math is just a really simple, basic overview of how we would do that interchangeability. It's all based on this idea of Thevenin to Norton conversion combined with going back and forth between V in and I in at the input. Okay, the next topic we're going to talk about is determining RI and R out. So RI and R out may not always be defined by the data sheet. So what do you do in the case where it's not defined? You can actually measure it, you can observe it pretty easily. So for example, if you want to calculate the input resistance at the terminals, and this goes for any device, you can apply an input voltage and simply just measure what the input current is, divide one by the other, and that'll give you your input resistance. You can also do the same thing for the output resistance. There are other ways of doing it using open circuit and short circuit tests, but the book focuses on this, so I'll talk about it this way. So we can calculate the output resistance by removing the source voltage, so whatever is at the input, applying a voltage to the output, and then doing the same thing, measuring what is the reverse current flowing into the amplifier, like this. So that's something that you may see in lab. It's also something that, again, if you're in the field and you have a device that is the data sheet's missing, or you have some questions about the way that it's defined, you can use that. Unilateral model is just really, it's a term. So a unilateral model is one in which the signal flows only from the input to the output, not in reverse. And we apply unilateral models to a lot of devices like amplifiers. There is some reverse transmission between the output and the input in an amplifier, but we don't use it in that manner. So our model is unilateral, right? We're looking at the output as it is affected by the input. We're not so much concerned with the reverse transmission. And our models, especially the ones that we have been using in ENG214 and ENG212, they don't even talk about reverse transmission at all. Okay, example 1.4. So this is an example from the textbook. It examines a bipolar junction transistor, which is represented by this model right here. Now, what is a bipolar junction transistor, a BJT? It's what we're going to study in Chapter 6. We haven't talked about it yet. And so at this point, we can just take the model at face value. And that's actually one of the really nice things about modeling, right? When you model something in an appropriate way, you can allow someone to use it in their design or in their whatever, however they want to use it, without truly understanding how it works. Which sounds like it's a bad thing, but it's actually, right, we want to boil everything down to a level where it can be used more robustly. So I give you this model. I say this represents how a BJT works, and then you can analyze the output-input relationship, the transfer function, the gain, all that type of stuff. So what do these different values mean? There's three terminals to a BJT. There's the base, there's the collector, and there's the emitter. Okay, and there's an internal value called the short circuit conductance, which is essentially the ratio of I out to V in if we short this to ground right here. And VBE is simply just the voltage between the base and the emitter terminals. We're calling the input resistance R pi, and the output resistance is labeled RO. So I've done the math and everything inside of the notes. However, I also did it by hand. So we'll take a look at it in the iPad and go from there. Every time. It says it's still hooked up. All right, so this is the example. We want to derive an expression for the voltage gain of the circuit below. This in the blue is the main part of the circuit. And in the green, what I did was I added the source, which is RS and VS in series. And then I added a load, which is RL, and so our output voltage will be the voltage across that. Okay, so how are we going to analyze this circuit? That's the first question I want to ask. We've done this several times where we've seen amplifier-like circuits where we have a dependent source, and what we normally do is split it up into two different pieces. So we're going to analyze the left-hand side first. So let's take a look at how the left-hand side works. The left-hand side, this right here, is a voltage divider. I made a joke in the previous class about how the answer to every question has been voltage divider, so we're just going to get signs that hold up and say voltage divider. So I'm going to stop asking questions where the answer is voltage divider. But this is a voltage divider. And so we're going to calculate the ratio between VBE and VS as R pi over RS plus R pi. Okay. Now we move on to the right-hand side. Includes all this over here. So this is a current divider. But just for the sake of being a little bit, showing some more techniques, I'm going to solve this right-hand side using KCL. Okay, you could just go ahead and use the current divider as well. So what I did was I defined 3 different currents. I called this IG down here. I called this IO right here. I called this IL down here. And so we know that IG plus IO plus IL will be equal to 0, right? They're all 3 currents heading out of the same node. So we want to get this in terms of V out. So we're going to make substitutions. What is IG? The direction of this agrees with the direction of this, so we have GM VBE. We plug that in down there, right? this is going to be equal to VO divided by RO. Remember what the passive sign convention means and how that comes into play. Does everybody remember what the passive sign convention is? Right, the passive sign convention is this idea here, that for Ohm's law, and I could draw a resistor, but really it could be any device, okay, the voltage across it is equal to the current times the resistance, assuming that this relationship between the direction of the current and the voltage polarity applies, right? So be careful when you're defining those values. If you don't satisfy the passive sign convention, let's say the current looks like this, then you have to make sure to account for it in your math. There's two ways of doing it. You can try to always adhere to the passive sign convention, or you can account for it like this. I normally try to adhere to it. Okay, so we're here at this point in the notes. We made the first two substitutions. The third substitution is that IL will be equal to VO divided by RL, so we put that in down there. And what we're going to do is we're going to take these terms, we're going to collect them together. So we have VO times 1 over RL plus 1 over RO plus 1 over RL. I took this piece and moved it over to the other side, which leaves us negative GM VBE. Then I take this piece and I move it over to the other side by dividing. Why does it keep moving like that? And so we end up with this expression here. This is not necessarily the way we like to represent things mathematically. Normally we try to stay away from fractions and denominators. And so I didn't show the steps, but if you were to multiply by the common denominator, et cetera, you would end up with this. RO, RL divided by RO plus RL times the rest of what's going on here. And so you're left with V out. This describes only the right-hand side. V out equals negative GM times this ratio times VBE. Now, if we want to find the value for the entire circuit, so the ratio between V out and VS, we take this value of VBE up here, and we plug it in down at the bottom. And so what that gives us is this final answer. Down here. Nothing really groundbreaking about this problem. I think that if you were to see this on an exam, maybe the use of the term BJT would throw you for a loop. But the real bottom line here is we're going to present things, especially this early in the class, in such a way that you already know how to analyze it. So BJT doesn't mean anything for this problem, essentially. And you should be prepared to solve problems like this. There's most definitely in the first exam going to be something along these lines. Cascading amplifiers, really something based around amplifiers gives us the best opportunity to mix what we learned in this chapter with stuff from before. Doesn't necessarily have to be an amplifier-based problem, but a problem where you apply KCL, KVL, and your previous skills. So hopefully you have all started on homework number 1. We're going to assign homework number 2 today, and you're refreshing those skills and going through all that stuff. All right. So you can see the problem is also done out in the slides if you're looking for an additional reference. in the end, this is what the circuit looks like. We can make some simplifications. We can pull this RO in as a parallel element with RL. We can flip the direction of the dependent voltage source, making the GM value negative. And it agrees with the solution that we got. Now we could plug in the numerical values, which I didn't do yet. If we plug in the numerical values, we end up with a value of negative 63 times. And if you wanted to get that in decibels, you could do 20 log base 10 of negative 63. This down here is just showing the effect of RO and essentially showing what happens if we eliminate RO and it increases our gain slightly to negative 67 times. Okay, so now jumping ahead a little bit to measuring the amplifier frequency response. So what is a frequency response? We talked about frequency spectrum already, right? Anybody remind me what a frequency spectrum is? So why don't I start off with one step back in terms of a question. What does a frequency spectrum describe? I'll give you choices. It describes a process. It describes a signal. It describes what I'm doing this weekend. It describes, what does it describe? Signal or process? Signal, right, okay. So if you think about, we have a time domain representation of a signal where the x-axis is time, and it's like what we see on an oscilloscope. A frequency spectrum is one where it shows us the strength of all the individual harmonics. Frequency response tells us how does this process affect those individual peaks. So hopefully this will switch over without making me put the code in again. Good. All right. So if we take a look at it, and let's say we have a frequency spectrum that looks like this. It's even all the way relatively. I'm not going to fill in what the exact values are. It's irrelevant at this point. I'm just doing qualitative demonstration. And then let's say we have a frequency response that looks like this. So what we have is the magnitude of the response, again, frequency. Can anybody tell me what that response is for? It's a circuit you've seen. It's not a voltage divider, and it's not a current divider. It's a totally new answer.
Is it a filter?
It's a filter. Now, which one? So the answer is, or the clue is, so the gain is high over here, it's low over here, which means it's letting what signals pass? Low, right? So it's a low pass filter, letting the low frequencies pass. Now if we take this signal, which is represented as a frequency spectrum, and we pass it through this process, which has a frequency response that like this, then what will happen to our signal, and I'm going to assume right here that the gain is 1, all right, what you'll end up with is it will take the spectrum and it will change its shape, right? Because this harmonic over here will be multiplied by a value that's much less than 1, bringing its height down. Same thing here, and then it returns to the normal height. So the frequency spectrum describes a signal in terms of its harmonic components. The frequency response describes how does a process affect those individual harmonics with respect to height, as well as we'll see in a second with respect to phase. So they go hand in hand, a lot like amplitude and gain, right? Spectrum and response. So how do we examine the frequency response? If it's not given to us in a data sheet, we can observe it directly by simply taking sine waves of given frequencies and passing it through the process. Okay, if it's an amplifier, then that's what it would be. So we pass 10 hertz, 20 hertz, 30 hertz, 40 hertz, keep on going, going, going. We look at the ratio between the input and the output, and then we can build our frequency response by simply graphing those or finding a mathematical expression that describes it. Can anybody explain to me why we have to use a sine wave? Why can't we use anything else? Why couldn't we use a square wave or something? So the problem with using essentially anything but a sine wave is that square wave, for example, can be decomposed into its own harmonic components. So the example I used in the last class is sort of like tuning a piano. Passing a sine wave is like just pushing one of the keys. All right? So you can hear what's specifically going on there. Passing a square wave through is like pushing 10 keys all at once, all right? Because that square wave can be decomposed into its individual harmonics, which then the response is going to affect each harmonic differently. Okay? So because the sine wave is the only signal that has no decomposition, right? The sine wave is just the sine wave. That's what we have to use in order to look at each individual slice along the frequency response. So the characteristic of sine wave applied to a linear circuit is unique because of its inherent nature. It can't be decomposed any further. So again, linearity has to do with this idea of the same shape coming out of our process that goes into our process. If we have a song, it should still sound like the song. If it's whatever, it should still have the same shape. Okay. Now related to that is the transfer function. So the transfer function is how we can describe the frequency response. It'll tell us how the magnitude changes with regard to frequency. So what's the ratio of the magnitude of the output and input, as well as the phase with regard to frequency. Is the phase of the individual harmonics shifted as frequency changes? So the transfer function doesn't necessarily have to be amplifier. Describes the input-output relationship of any device or process with respect to various parameters, including frequency of input applied. It's a complex value, often defined in terms of magnitude and phase shift. If we wanted to, we could also describe it in terms of its real and imaginary components. Although the problem with that is it's not, the physical effect of that is not as obvious, right? We know what increasing or decreasing magnitude means, what it would look like on an oscilloscope. We know what phase shift means, what it looks like on an oscilloscope. Changing the real and imaginary components is a little bit less practical, for our purposes at least. Okay, bandwidth of a device. So what is bandwidth? Right, this is a term that I'm sure you guys have all heard. It's a term that gets thrown around a lot, like in the business world. What's the bandwidth of, our company and all that type of stuff. But here we're talking about the engineering meaning of bandwidth. So can anybody, without reading what's on the screen, throw out what their little definition of bandwidth might be? Okay, so it has to do with frequencies. It's the range of frequencies over which the magnitude response is constant or within 3 decibels of being constant. So if you think about a frequency response that looks like what's on the next page, this right here. Let's say that this is an amplifier. Amplifying a song. We keep using the same example over and over again. So the bandwidth spans from here to here. This is our maximum output, and this is 3 decibels, even though it's not labeled. This is 3 decibels down from that maximum output. So what we're going to say is that anything that passes through this range is going to be amplified by more or less the same amount. So we have a linear process in here. Once we get outside of here, it becomes more nonlinear, and we can expect the shape to change. So if we want our song to sound the same when it comes out as when it comes in, we better make sure that this bandwidth is large enough to cover all of the audio frequencies that you can hear. Okay? Or else, we have a nonlinear process, it'll affect your shape, and then things will get distorted. So that is the reason why bandwidth is defined in this way. We want the process to be linear. In order for it to be linear, all the gains for the individual frequencies along the spectrum need to be more or less the same, and the bandwidth tells us that range over which the gains are more or less the same. Now, this would be a good question to ask you on that oral little quiz thing that I'm going to try to do after the exam. What does the bandwidth of a device mean? Again, I don't want anyone to get too anxious about it. It's going to be real short. For most people, it's going to be like a 20-second answer, and you're going to be on your way. So this is really what I want to take away from it, and that's the reason why it's worth a significantly smaller amount. But I think that one-on-one, that face-to-face, it'll give people who maybe don't do so well in the written another opportunity to show that they have a knowledge base there. So that's really all it's going to be as far as that oral quiz goes. It's going to be a question like this. If you're paying attention in class, if you're doing the homeworks and just familiar with the material, that should be stuff that you should be able to throw out. And I'm going to keep it to topics like this that are mainstays of what we discussed. Okay, this is your second homework. Rolling homework deadline. It's always due a week after it's assigned. I will try to say that every time, but that should just be the assumption. If I assign it on a Friday, it's due on a Friday. Assign it on a Tuesday, due on a Tuesday. All right, so now we're talking about frequency response, and the place where we have already discussed frequency response is a little bit in ELC251-02, more in ELC214 when we did low pass and high pass filters, right? A low pass and a high pass filter both fall within this category of single time constant networks. The reason why it's called a single time constant network is because it only has one reactive element. Okay, that's hence RL, resistive inductive, RC, resistive capacitive. Actually, in my section of ELC212, we started talking about second order time constant networks, right? And that was one where we had RLC, and we saw that the math was different. But so low pass and high pass filters are single time constant. First order, represented by a first order differential equation. Okay, so low pass filter, as you already well know, attenuates output at high frequencies, allows lower frequencies to pass. High pass filter attenuates output at low frequencies and allows higher frequencies to pass. So they are opposite of one another. Time constant describes the length of time required for a network transient to settle from a change. It also describes sort of the cutoff between the range where signals are allowed to pass and where signals are not allowed to pass. And we'll get a little bit more into those details in a sec about exactly what the time constant describes. So these are figures for the low pass and the high pass filter, the RC version of it. Again, we can create RL versions that use inductors. And the only difference is just switching the position of the resistor and the capacitor. Okay, for the low pass filter, the capacitor, the output is measured across the capacitor. For the high pass filter, the output is measured across the resistor. These are voltage dividers, okay? The only difference being that instead of it being two resistances, we have a resistance and a reactance, or two impedances. So if we wanted to analyze, which we will in a second, how this circuit works, we could use a voltage divider in order to analyze that. So this is what the transfer function, both transfer functions, sorry, for the high pass and low pass filters look like. So, and with a little bit of derivation up top. So let's try to explain this. First things first, we know obviously we're looking for V out over V in. V out over V in. Okay, good. Now, let's give these generic names. I can call both of these R impedances, right? A resistance, a reactance, it all falls into the term impedance. Hopefully, you all remember from oh man. All right, so I'm learning my lesson. I cannot switch quickly back and forth between these two. All right, forget it. I guess I could leave one up on one screen and the other one. Anyway. So, all right. Returning to what I was saying a second ago, we can represent both of these as impedances. Impedance is equal to what? Anybody remember? It has two components. Yes?
Real and imaginary.
Yes. So then take it one step further. What do we call the real part? Okay. What do we call the imaginary part? It's not up here. Reactance, right? Impedance is equal to resistance plus J times reactance. Reactance we represent with an X. Now, so what we have here is Z output over Z, what I call Z input over Z output. So this is Z input, this is Z output. And then they're named the same here. So on this end, the capacitor is Z input. On this end, the resistor is the Z input. But anyway, you can see this is just a representation for a voltage divider. So hopefully everybody understands how we go from here to here. Now, how do we go from here to here? What happens? Where do we get this 1 over J omega C? Yeah.
That's how you find the impedance of the capacitor.
Exactly, right? There's two expressions we can use. The reactance, which is equal to the impedance of a capacitor, because there is no resistive component. At least we assume there isn't. Okay, so the impedance across a capacitor, or the impedance of a capacitor, is equal to the reactance of a capacitor, which is equal to 1 over J omega C. Okay? Omega is the frequency of the signal that's applied across it, and C is the capacitance. So what you see here is that if we have Z out over Z in plus Z out, we have 1 over J omega C plus R plus 1 over J omega C. So all this is doing is taking our voltage divider and plugging in the values that we already know for the reactance of a capacitor. And the result is, as you would expect, this is proportional to some constant times 1 over omega, meaning that the gain gets smaller as omega gets bigger. Over here, this part is exactly the same. Z out over Z in plus Z out. The only difference is that now our numerator is R, as opposed to being 1 over j omega c. And so when we find what this is proportionally equal to, or proportional to, we end up with k omega, and that's the reason why the gain increases with frequency. So there is a homework problem that goes into more detail with this. And we can go over that if you'd like and get into the nuts and bolts. So one note about homework. I don't set aside a time to do homework problems. You can ask at any point. Okay, it makes most sense to do it at the beginning. So like, for example, your first homework is going to be due on Tuesday. When you come in, if you have a homework question, just at the beginning, even if I start talking, just say, hey, before you start, can we see homework X, Y, Z? And I'll be more than happy to go over it. Okay, so like I said, there's a homework problem that dives more into this, and that's a good time, I think, to spend some more time going over that stuff. Okay. Now, this is cryptically written because I took this from our cheat sheet where I didn't tell you which one's which, but you can see that this is the low-pass filter over here, and this is the high-pass filter on the right-hand side. So the transfer function for the low-pass filter is this value k. It's the transmission or the gain at very low frequencies, at DC frequencies, over 1 plus S over omega 0. What is S? S is j omega. That's just another way of writing it. Okay? And what is omega 0? This is what we call the corner frequency for the low-pass filter. So here, this is the corner frequency. This is essentially the inflection point at which the gain begins to decrease. We also use the term corner frequency over here for the high-pass filter, which is the point at which the gain flattens out. So if you're looking at this transfer function right here, it should give you a pretty good idea of what's going on in the filter, or how it works. K, the numerator, will tell you if you just input a DC signal, a flat line to it, what would be the gain? Okay, what would you get out? And it also tells you what is your cutoff frequency for the low-pass filter, meaning, let's say you're trying to eliminate a harmonic at 1,000 hertz. You want to make sure that this cutoff frequency is lower than that, right? Because you want it to be lower than what it is you're trying to get rid of. Now, what we can do is we can take this transfer response right here, and we can find the magnitude of that response as well as the phase of that response. The magnitude simply is the ratio of the height, right, the magnitude of the waves, and the phase response tells you how the phase shift between the inputs and outputs will change. I already told you what K is, and transmission at very high frequencies will be equal to 0. Over here, similar sort of setup, except our K, instead of meaning the transmission at very low frequencies, which will be 0 for a high-pass filter, this is the transmission at very high frequencies. So we have Ks over S plus omega 0. S, again, is j omega. Omega 0 is still our cutoff frequency. So if we're trying to cut out a lower frequency, let's say 10 hertz, now we better make our cutoff frequency significantly higher than that, right? Because the low part will be cut off. So if we're trying to get rid of 10 hertz, we want to make sure our cutoff frequency is 100 or 1,000 hertz, somewhere along that line. This is the magnitude of the response. This is the phase of the response. And so these are what the responses look like in a graphical form. So we have the low-pass filter. Again, low frequencies, the gain will be equal to K. At the cutoff frequency, we have the inflection point, and it begins to go downward at negative 20 decibels per decade. So what does that mean? What's a decade? First question. A decade just means going from 100 to 1,000 hertz, 1,000 to 10,000. This scale down here is a logarithmic scale. It doesn't go 1,000, 2,000, 3,000. It goes 100 hertz, 1,000 hertz, 10,000 hertz, etc. Over here we have the high-pass filter. Again, this is the cutoff frequency. So you have to read the x-axis very carefully. The x-axis, what it's saying is omega over omega 0. So 1 is omega 0, right? Frequency is omega 0. Frequency is the cutoff frequency. Over here we have 10 times the cutoff frequency. Over here we have 1/10 of the cutoff frequency. And every dotted line would be, so that's 10 times, 100 times, 1,000 times, etc., etc. So over here at the cutoff frequency, we have the inflection point. It continues downward at negative 20 decibels per decade, or positive, I guess, because it's going upward, all the way back. And then it stays flat. Now, we haven't talked about the phase response that much. For the low-pass filter, the phase shift at the corner frequency is negative 45 degrees. So what that means is, if you have a low-pass filter and you put in a sine wave at that frequency, okay, at the corner frequency, the output you get will be shifted 45 degrees from the input. For a high-pass filter, negative 45 degrees. For a high-pass filter, the value is positive 45 degrees. So if you put in a sine wave with the same frequency as the corner frequency, it'll be shifted by positive 45 degrees. For the low-pass filter, as you go higher and higher, the shift will move towards negative 90 degrees. As you do it for the high-pass filter, it'll shift to 0. So in one sense, it makes sense to look at this point right here. What happens when you put in a very low frequency into a low-pass filter? The gain will remain unchanged, and the phase will remain unchanged, right? It's at 0. For a high-pass filter, for very high frequencies, the gain remains unchanged, and the phase remains unchanged. I'm not expecting you to memorize these figures, okay? Going back to sort of the philosophy behind this class, I don't really think memorization is a huge part of what it is that I'm trying to teach you. But if I give you these graphs, and I ask, let's say I demonstrate a certain point, or I ask you to tell me, this could be a short answer question, and tell me what is the gain at 100 times for this low-pass filter. What is the gain at 100 times the corner frequency? What's the answer? So 100 times the corner frequency, this is 10, 100 would be right about here. Okay? We know that the slope is going down at 20 decibels per decade. So it goes from 0 to negative 20. When it got to 100, it would be at negative 40. So that would be the answer. Okay? If I asked you what is the gain at 1/10 of the corner frequency, the answer would be 0 decibels or 1 time gain. Over here, similar sorts of questions that I could ask. Yes?
What do you mean by when you say corner frequency?
So corner frequency is the same value we defined in here, omega 0, all right, which if you recall back to ELC251-02, we defined that it's equal to 1 over RC. So it's a value. The best definition of it is in this figure here. it is the point at which we have a separation between filter, a signal is allowed to pass, and signal is beginning to be blocked. And then mathematically it's defined as 1 over RC. So we control it by the ratio of the resistive and the capacitive values. Okay? Like I said, there's a homework problem that deals with this. If you want to ask me about that homework problem, I'll be more than happy to go more into it. But these 3 slides together, more or less, give the information at face value. This is the description. These graphs give you a description of how it works, and the mathematical equations on the previous page present that in a mathematical form. We could spend a lot of time deriving it, but it's not necessarily what we're tasked with here today. So we'll come back to this when you address that homework problem, and we'll have another chance to take a look at it. Why don't we try a couple more of these? Let me ask a couple more. So, okay. What is the gain, okay, for the high-pass filter at its corner frequency? K. Yes, exactly. So this is the high pass, and the gain right here is K, which for the high pass filter, actually K is equal to 1 or 0 decibels. You'll note here that it says 3 dB. There's 2 ways of drawing this figure. There's the ideal way, which has this sharp inflection point. It actually curves a little bit more. Honestly, for the purposes of this, I'll accept either 0 dB or negative 3 dB will be fine. What is the phase shift for the low-pass filter at 10 times corner frequency? Again, just reading, it all comes down to just being able to read these graphs. Phase shift at 10 times, which one did I say, low or high pass? Low, for low. Yeah, it's close. It says about 5.7 degrees off, but again, I'll go with the ideal, it's fine. So negative 90 degrees. So hopefully these type of questions, are leading you in the right direction. Understanding how to read these graphs is about understanding frequency response and not necessarily anything that's even specific to the low or the high pass filters. Does everyone feel good enough about this to at least move on, and then we can, like I said, we can try to revisit it again if there's serious questions. Okay, so next, and this is a good example because this will this will reinforce some of the topics we were just talking about. Example 1.5, voltage amplifier. It says examine a voltage amplifier with an input resistance as well as an input capacitance, a gain factor of mu, and an output resistance of R naught or R out. Derive an expression for the amplifier voltage gain, VO divided by VS, as a function of frequency. From this, find the expressions for the DC gain and the 3 dB frequency. So this is good. This will be a good opportunity in order to dive more into this. So this one I am going to do on the iPad. All right. So, this example. solve for the voltage gain, and then I'll write the rest later. So essentially we're just solving for the voltage gain of the circuit below. Okay. So the circuit looks like this. It's very similar to what we've seen so far. It just has this additional little capacitor added into it. So this is our this is RI, this is called CI, this is also the input voltage right here, this is called VS, this is called RS, and then we have the output stage, which we will call mu times VI. So that's that gain constant that we were talking about a second ago. We have our output resistance. And then lastly, we have our load. Okay, so the amplifier itself really falls from here to here. And then over here we have the load, and over here we have the source. As we go further and further, I'll stop saying stuff like that over and over again, but since we're still sort of in the beginning, I'll keep reiterating that. Okay, so first step here is going to be to analyze the input stage. Okay, which is going to be done as a voltage divider. Yo, sorry, I couldn't hear you. If I can't see you, sometimes you have to just like throw a tomato or something.
But how do they like affect each other if they're not connected?
Essentially through this. It's just like all the other amplifiers that we saw. So the voltage of the dependent source is dependent on the input voltage. Now this is a model again, so that's magic essentially, right? The model doesn't give you any justification for how it's affected. If we were examining a real amplifier, there's transistor-based design, and we actually are going to get to that in this class. We'll see more towards the end on what the physical effect is between those two, but we haven't gotten that far yet. So right now, it's just this magical relationship between the dependent source and the input. All right, so in the simplest form, I know we're getting sick of this, voltage divider, again, VI equals VS times, and what I'm going to do is I'm going to group these two together for a second. And I'm going to call this ZI. So we haven't defined exactly what it is. I'm just saying that we can put these two together in parallel and call it ZI. We know that we can combine impedances in parallel, so we will be able to do it. But we haven't gone through the math yet. So VS is equal to Zi over Zi plus Rs, right? Rs is the same as Zs because, right, there's no reactance. And actually, let me write the equation that I didn't have a second to write before because the iPad wouldn't switch over. Again, right, impedance is equal to resistance plus J times reactance. So we have impedance we have resistance, and we have reactance. Admittance is equal to conductance plus, then we have here is called susceptance. And the relationship between the two of them okay, so that's the whole gambit of everything you need to know for complex values related to impedance. We'll be using those terms a lot. Hopefully you can get familiar with them quickly. Okay, so now going back here for a second. So we have this equation. All right. We can't really do much with this until we figure out what this value is. We don't know what Zn is. Right? So a little mini step that I'm going to put in here, I'm going to say I'll call it step 1b, is to calculate Zi. And the little arrow above the Z, all it represents is that's a vector. It's a complex value. So Zi is equal to the parallel combo of Ri and I'm going to be more formal. So I'll give these names too. This is the impedance associated with that I'm going to call Zci. And the impedance associated with that I'm going to call Zri. So Zi is equal to the parallel connection of Zri and Zci. We know how to calculate a parallel connection of two resistors. It's the same thing for two impedances. It'll be equal to Zri Zci over Zri plus Zci. Okay. Now, what is Zci? We talked about that a second ago. What is the impedance of a capacitor? 1 over j omega c. And this is just going to be R. So what we end up with is Ri times 1 over j omega ci over R plus 1 over j omega ci. We are going to try to do what we can to clean this up and take the fraction out of the denominator. And so in order to do that, we can simply multiply this term right here. We can multiply this by j omega ci over j omega ci, right? Because that's equal to 1. And so what that'll leave us with, this will help us with finding a common denominator. We'll end up with Ri 1 over j omega ci. This is not changing. The numerator will change. We'll have R times j omega ci over j omega ci plus 1 over j omega ci. Now you can see that we can combine these two terms together, right? Because they have a common denominator now. And so what that'll leave us with is, again, the top still hasn't changed, but the bottom will be j omega R I C I plus 1 over j omega ci. And what ends up happening is that these will cancel out with one another. Okay, because we have a 1 over j omega ci in both the numerator and the denominator. And what we're left with in the end is Ri, I keep forgetting to add the I, Ri over j omega Ri ci plus 1. Okay, I don't think we're going to finish this problem today, but we'll get as far as we can, and then we'll pick up with it next time. Okay, now, what I'd like to do is just try to get the input stage done. So this is Zi. So we can take this, if I can zoom out for a second, we can take this value right here, and we can plug it in right here in the Zi up above. Right? So our second step is going to be to combine, or maybe the better way to put it is insert Zi into our input stage equation. So that will leave us with Vi is equal to Vs Ri over j omega Ri Ci plus 1. This is going to look a little bit messy. Ri over j omega Ri Ci plus 1 plus Rs. So if you remember, this was our Zi over Zi plus Rs. That's what we did. Okay, so really quickly, we're going to do the same thing that we did before in order to clean this up. And this is the one time I'm going to go through all the nitty-gritty of this math. You have to, for better or for worse, learn a lot of these. I mean, it's algebra skills that you should have gotten a long time ago, but I mean, I know you don't use it a lot sometimes, so they can get a little bit rusty. But trying to do these types of simplifications is going to come up in this class relatively often. So how do we get the fraction out of the denominator? What we're going to do, again, is we're going to multiply this by j omega r I c I plus 1 over itself. Because that's equal to 1. And that's going to allow us to get rid, or it gives us a common denominator with what's on the left. So what we end up with, and I'm just going to say Vs, and then I'm just going to write top, whatever's up top, because some of that stuff we can just go back and get it later. Okay, so that will leave us with Ri plus Rs all over J omega Ri c I plus 1. Okay. And I shouldn't have taken that shortcut because it messed me up. So I'll put this back. We have our Ri over J omega Ri c I plus 1. I know we're close to the end here. Again, this will cancel out with that. And what we'll be left with is Vs times Ri over Ri plus J omega Ri Rs Ci. And yes.
What happened to RS?
He's still there.
Okay, I didn't.
Yeah. I switched his spot.
No, because you have a +1. You have to distribute it.
Yes, you're right. I'm trying to do it quickly here at the end, and I'm. Okay. Well, we have to stop here because we're at the end anyway. So it's not the best stopping point, but we'll pick up from here. We'll finish this example. We're definitely going to finish Chapter 1 on Tuesday and hopefully get some significant amount into Chapter 2.